Franklin Orr. Lynn holds BSc and PhD degrees both in chemical engineering from Stanford University and University of Minnesota. He's a professor at Stanford Department of Energy Resources Engineering since '85. He has been department chair of his department and also served as dean of the school. And he was former Under Secretary for Science and Energy of the US Department of Energy between 2014 and 2017. Lynn is a member of the US National Academy of Engineering, and I'm quoting from them, for contributions to understanding of complex multi-component flows in porous media and its applications to the design of enhanced oil recovery processes, and for superb academic leadership. He has received many awards, hard to bring all of them here, among which a Stodullah Medal of ETH Zurich, Exceptional Service Award of the Department of Energy of the US, IOR Pioneer of SPE, and Honorary Doctorate in Engineering from Heriot-Watt University can be also mentioned. His Google Scholar page lists most of his publications and co-authors. Please take a look, especially his groundbreaking work on carbon capture storage and climate related topics in prestigious journals such as Science. He was director of the Precourt Institute for Energy at Stanford University from its establishment, and he served as director of the Global Climate and Energy Project, again at the same university. He has had almost 30 board memberships in different committees and professional organizations. For example, he served as vice chair of the board of directors of the Monterey Bay Aquarium Research Institute until 2014, and again joined back since 2017. He chaired the advisory panel of the Packard Fellowships for Science and Engineering until 2014, joined back again to the same board in 2017, and was a foundation board member for 9 years of the same organization, company. He's a member of the Climate Works Foundation Board of Directors. Importantly, he has advised many students, some of them I know, some of them you all know, established plenty research consortia related to carbon capture storage, especially at Stanford, during his role as a unique professor and a role model to many I know at the Department of Energy Resources Engineering at Stanford. We are pleased and honored to have him here as a keynote lecturer hosted by our Faculty of Civil Engineering and Geosciences at UDelft. For this to happen, he did not just prepare the talk, but also spent several hours to make sure the online conference system would work. So we admire his efforts to allow us hold this seminar, which is not only for science, but also to have us all connected during this disconnected period. Please join me, welcome Lynn. His lecture would last for 30 minutes. I would like to ask the audience, please mute yourself during his lecture, but as long as the network is okay, keep your cameras on, because it would give the chemistry of a lecture to our speaker. And after that, we will hold question and answering part. And I would like you please type in your questions, because we might have plenty audience in the room. And then I'm gonna go through them all. So I'm just going to admit other people. We have about 92 people right now hearing you, Lynn, please.
Well, good morning. Good morning here. Good afternoon there. It's a pleasure to be with you. I see some familiar faces amongst the video screens here. So hi to friends, and thanks for putting up with me learning how to do this via Zoom. We had a week of at the end of our winter quarter of training on this as we moved classes to online. So we're probably learning the way I think everyone else is. So my topic today is just it's really the broad one of how do we move the world's energy systems to ones that really fit much better with the way the planet works and how we live on it. So if you think about the challenge that we're trying to satisfy, modern societies have energy woven through them in every aspect of life. And so we need energy systems that are clean, that are abundantly available, that are affordable. Energy costs feed through the entire economy, and that are reliable and resilient to both to natural system attacks like hurricanes and tornadoes and earthquakes, but also the kinds of cyber attacks that have sometimes been made as well. So this is a challenge, but it's also an opportunity to create and manage linked, very complex systems that deal with all the challenges simultaneously. And I think even as we focus on climate and meeting the challenge of lower greenhouse gas emissions, we can also do much better on energy services and also on the kinds of other air pollutants and water pollutants and that sort of thing as well. So there's an opportunity to make life better all around the planet. So the question is, okay, how do we do this? And I'd like to make the argument that there is no shortage of energy. There is plenty available, and I'll try to back that up here in a second. It's all about how we convert those energy resources into some energy service that we need. And an example would be that right now in the world, we use lots of electricity. It's generated mostly by fossil fuels, natural gas and coal for the most part, to generate electricity. And then that feeds through the rest of the system. But there are plenty of other resources that we can manage, that we could use. So here, this chart is an attempt to portray the energy resources that we might use. And you'll be pleased to know that I'm not going to go through every number on the slide, but let me just give you a few examples. So the big, I'm hoping you can see my cursor, that these big fat arrows are flows of energy. The number is in terawatts, so that's power, that's energy per unit time, an average flow. Solar radiation, for example, coming into the planet is 162,000 terawatts. Now, if you look at the bottom right of the slide, you'll see that we humans use about 18 terawatts now. That's the average power across the planet. So you can see that the incoming solar radiation, of course, is many times greater than that. That solar radiation gets partitioned. Some is absorbed in the atmosphere. Some comes down to the surface. Some of it evaporates water. That's the source of hydro electricity resources. Some of it goes to surface, warming the surface. That's a good thing. And if you follow that little black arrow all the way through, you can see that we use about 0.4 of a terawatt of hydroelectricity out of all those resources that are there. Wind energy, these numbers are a few years old now, so the wind energy makes a big resource, but we only use a small fraction of it. And then there are also stored energy resources. So these ovals represent the amounts of stored energy in that favorite unit of everyone's, zeta joules. That's 10 to the 21st joules. And in case you don't carry that number around in your head, we use about half a zeta joule per year. So you can see that the energy resources are all big compared to the amounts that we use. It's really about converting those resources by some technology in a way that we can afford. So plenty of energy, let's get to work to transforming it. Well, we humans have been doing this for a long time. And an example is engines. That really started with the steam engine. So invented at about 1700. The interesting thing here is that if you think about look at what the efficiency of that first steam engine was, it was about 0.5% efficient. But it was a magical device because what it did was to allow people to build a fire and then convert that into mechanical work. And in some sort of ironic system, the first steam engines were used to pump water out of coal mines. Now, since then, of course, a lot of engineers have worked on other ways to convert energy. And if you jump forward to now with something like a solid oxide fuel cell and a gas turbine at the end for recovery of additional waste heat, efficiencies up in the neighborhood of 70% are possible, with lots of other possibilities in intervention diff kinds of engines. So over that 300-year period, efficiencies have increased, and the opportunities to apply the conversion to mechanical work have expanded dramatically. Now, so this is the kind of thing we need to do for all those other energy resources as we go forward. Now, it would be good to pick up the pace because this all took 300 years. But even so, it illustrates the kind of thing that we need to do as we deploy systems at big scale. And scale is the subject of the next slide. That is that if you look at the history of things like lots of devices that we've used and things like photovoltaics or transistors or LEDs, those kinds of things, as we move to systems with larger scale of the practice of making them and using them and operating them, designing them, costs for the most part come down. So one challenge is to get new technologies to a big enough scale that we get far enough down the learning curve that they can compete with large existing systems. We have energy systems now that are based on fossil fuels that are relatively inexpensive, and so that new devices have to compete with that sort of problem as well. So you say, okay, we're convinced. Let's think about how do we get to the next stage of energy systems. So this is my sort of simplified personal roadmap. We need to deploy energy efficiency everywhere. Energy that we don't use is frequently the cheapest to supply. We need clean and abundant and very low cost electricity. That underpins absolutely everything else. And we humans have been busily electrifying the planet for the last 150 years, and that I think will continue. We'll want to electrify more energy services, heating and cooling, transportation, those kinds of things. Many of them can be accommodated with using electricity. And then we need, especially in the United States, I think Europe's better off than we are, but we need to improve the grid that distributes all that electricity to accommodate the intermittency that comes with some renewable energy resources and bolster resilience. We're probably going to need to deploy carbon capture and storage for some portion of the energy system. And then we should have a vigorous and broad-ranging portfolio of new technology R&D. So I'm going to just try to say a few words about each of these topic areas as we move through this. So let me talk first about efficiency of building systems and technologies. And by the way, here I'm drawing on work that was done by many colleagues at the Department of Energy when I was there. We did something called a quadrennial technology review, where we really tried to look across the technology landscape and ask ourselves, where were the research opportunities to move to cleaner systems, and as a prelude to thinking about the portfolio of research that the Department of Energy would support. So I'm stealing heavily from that. So I just would make the point, I'm sure, we all know this, but it's worth even just remembering this, that no energy device is 100% efficient. Carnot showed that thermodynamically. And we should remind ourselves, though, that good systems often have efficiencies better than 50%, and that's the chain of efficiencies that really matters. So if you think about incandescent bulbs, I'm sure that none of us have those anymore, but there's still quite a few around the world. If the original power plant efficiency might be 35% for a coal-fired power plant. The transmission may be 90% efficient. The light bulb is maybe 4% efficient. So the front to back overall efficiency is only 1%. Now, if you can do better with compact fluorescence, with LEDs now, you can do better than that by quite a bit. And if you use a 60% natural gas combined cycle plant plus LEDs, you can get that whole system up by more than an efficiency by more than in that order of magnitude. And if you think about heating and cooling and building systems, there really are lots and lots of opportunities. Buildings are complicated systems, and one thing we've learned at Stanford is that by designing carefully and operating carefully, you can without really major investments cut the energy use in buildings by about half. Takes more effort to get beyond that, but by golly, we can make a big difference there. Lots of opportunities within buildings, windows, lighting, more efficient heating and cooling and refrigeration and those kinds of things all offer opportunities to do much better. So we should be taking advantage of all of those. All the studies that I've seen suggest that the lowest cost reductions in greenhouse gas emissions come from applying energy efficiency. Now, I will say that Europe has been much better about this in general than the United States has. The politest way I can say it is that in the US, we have left ourselves a lot of room to do better, but we should be doing that now. And the good thing about all of this is that most of these kinds of efficiency efforts will pay for themselves in relatively short time and reduced energy costs. And I know from my own house when a few years ago when we decided we would install some solar cells to make our own electricity at the house, that caused me to go pay attention to the electricity bill. And as I did, I was sort of appalled. And that set me to work of figuring out where the electricity went in our house. And by the time I was done with all that in my watt meter, I had reduced our electricity use by about a third with a capital investment of maybe $100. So it really was about how we operated the building and paying attention to lighting and turning things off when they weren't being used. And that suggests, I think, that there's a lot of room to do better here and that it will save everybody money if we do. There are some systems, again, Europe has done this much better than others, but Stanford in recent years, we replaced a natural gas combined cycle plant with a heat pump system plus direct solar access that saves hundreds of millions of dollars over the next few decades in reduced fuel purchases, reduces our water use, and reduces our CO2 emissions by about 70%. Now, the way this works is that all year round, we take heat out of buildings with the chilled water loop. And in some cases, then we put heat back in. Now, it's different in winter and summer, of course. But because there's an overlap there, using big heat pumps to remove heat from the chilled water loop, that's taking it out of buildings, and pushing that back into the hot water loop instead, means we don't buy fuel for that, and that both reduces emissions, reduces costs in a way that saves a lot over time. Now, district heating and cooling has been used in other places in the world, not so much in the United States, but for a campus-size operation, it actually works quite well. And because the cost of solar energy has come down so much more than we expected when we designed this system, it actually is performing economically even better than predicted. So there are big opportunities there. So let me move into clean electric power. So, we really do have to, if we want to move the needle on greenhouse gas emissions, we need to electrify energy services and get to cleaner power. Now, a first step in this is to replace coal-fired power plants. We have had lots of them in the U.S. With natural gas. That's been helped by the relatively low price of natural gas in the United States. the advantage comes from two things. One is the reduction of carbon in the fuel per kilowatt hour of thermal energy. And the second is the better efficiencies of a combined cycle natural gas plant. So just that conversion alone can give you about a 70% reduction in CO2 per kilowatt hour. And I'll show a new design of a burning with pure oxygen and carbon capture that can be applied in principle to natural gas systems as well. Using, now some of course would argue that we should stop using fossil fuels altogether. I think it makes sense to use natural gas both in the transition and to some extent as firming for intermittent renewables, but with carbon capture in the future. Now I will say that absolutely essential portion of this is eliminating methane leaks, because methane of course is a much more powerful greenhouse gas than CO2 is, and about a quarter of the radiative forcing in the world now comes from methane in the atmosphere. Energy use is only a portion of that. Agriculture is another big source, but at the same time eliminating leaks, that's something we know how to do, and new sensor technologies can help us detect those and deal with them quickly. Now, an obvious thing to do is to use the big solar and wind resources. In this graph is from 2016, but the world is building lots of new renewables in big quantities. Now you have to be a little careful here because quantities of power additions are often quoted in nameplate, that is maximum power from the system, and no solar system or wind system operates at 100% capacity factor. Solar might be 20% typically, and wind 35 or 40%. But nevertheless, those are big resources and ones that we can put to work. And they are now, for the most part, competitive in many places, in good resource places with no subsidies. So there's substantial growth there. This last year in the U.S., wind power exceeded hydropower as in terms of total generation. And this is another example. I made the argument that improved efficiencies come with time. I know this is impossible for anyone to read, but if you look at the general curves, this is plots. These are plots of cell efficiency versus time for a whole bunch of different kinds of solar cells, and you can see that they all move up and to the right, which means that the cells have become more efficient over time. Now, this doesn't say anything about cost yet, but efficiency combined with cost reductions at scale can really make a big difference. So lots of opportunities there, and plenty of opportunities, I will say, for future material science that can produce better efficiencies with earth-abundant materials at relatively low cost. So lots of research going on there. Manufacturing has really reduced costs of both wind and solar, and things like LEDs and batteries are marching down the learning curve. Just over the past decade or so, LED costs have come down by better than 90%. Utility scale PV costs by more than 50%. And so there really is an opportunity to do better as we get to scale. Now, all these technologies have to get to the point where they're being dealt with at that kind of scale, and that's the place where government subsidies and so on can help make that transition. But eventually, these systems have to compete on their own, and that's what we should aim for. If you look at estimates of future wind and solar costs, IEA has done a bunch of these kinds of estimates, and you can see that these costs are comparable to what new generation by more conventional means would cost. So, as I say again, these renewable technologies are competitive in the cost structure of current energy systems. Now, one thing we did at DOE too was to look at what's the option for the future. Again, this is a few years old, but if you look at the composite elements of costs that go into the installed cost of PV systems, there were at that time sort of in the 6 or 7 cents a kilowatt hour. We could see plausible pathways, that is, and multiple routes. So it didn't just require miracles at every stage for getting down to the 2 to 3 cents a kilowatt hour, particularly in good resource areas. And that's important because if you have costs that are that low, then you can afford another energy transformation. So for example, you could think about having, converting that clean electricity into, well, using energy storage, which some of it could be in terms of chemical bonds. So you can think about making fuels. So there are really lots of opportunities if you have very low cost solar. Now, in the United States, at least, nuclear power is almost 20% of our generation. It's once you get past the cement and steel that goes into the plants, they have very low CO2 emissions, and they have high capacity factors. The problem in the U.S., at least, is that they are not currently cost competitive. Our markets, for the most part, are dispatch markets, which means that that people who are selling power bid for a price, a cost of operation, and then they get dispatched based on who offers the lowest prices. The nuclear plants, particularly the older ones, have a hard time competing in that. There are some new options out there. I'll show an example in the next slide. And research underway, but right now nuclear, at least in the US, is having trouble competing. Now, in other parts of the world, China is building quite a number, 20-odd nuclear reactors, and there are R&D opportunities here. For the US, at least, we have not solved the waste storage problem, and siting and licensing, and particularly construction costs are a big issue. Now, the next sort of intermediate stage of availability of nuclear power, there's one design that it's a small company called NuScale for a small modular reactor. These are kind of 50 megawatt electric modules. They're a simple design. They use thermal convection, no pumps. The device sits in a pool surrounded by a pool of water that's sufficient to cool it to cold shutdown, even if all power is lost. And control rods drop in by gravity. It's in design certification in our Nuclear Regulatory Commission now. And that's certification looks like it's likely to be complete this year. And there are 2 projects that look like they're going to go forward. One to be located at a DOE National Lab, Idaho National Lab, supply power for Utah, and another one at Oak Ridge. And we'll see how they do on cost. In principle, these should be manufacturable in a factory if they can get enough orders to survive to that level. Remains to be seen on that one. There are some other schemes around too. A week or so ago, I had a chance to visit TerraPower, the Bill Gates funded operation that's looking at traveling wave reactors. They're quite a long way from the design for certification, however. Now, if we have all this clean electricity, of course, we have to distribute it. And the grid that we need in the future needs to be pretty different from the one we have now. We basically have a system that is mostly radial, that is a modest number of relatively large power plants distributing across a grid that then fits out to the edges. The future grid will be much more interconnected. It will be much more distributed generation with varying power qualities and the need to manage where power goes more directly. Lots of opportunities here to provide both better services and lower cost and improved resilience. And one thing that happened during the the last big finances in the U.S. was investment in a whole bunch of synchrophaser sensors to allow measurement of where power flows were going and phase angles and reactive power. And that will give much better control over the grid. We're more resilient now than we were before. And research on solid state transformers and active controls with wide bandgap semiconductors will offer opportunities as well. So better grids are out there. These are complicated systems, and they need to be managed in ways that we're going to have to learn to do better. And I just will say that for those who like to think about all of this, the world is really built with a system of very complex systems. They are, think about electricity, think about fuels, think about water, think about sewage, transportation. All these systems are interconnected. They have different latencies. They have different spatial scales and time scales. They are truly inherently multi-scale problems. And we're going to need better systems that have lots of automatic controls. Right now, we control the grid mostly by turning power plants on and off. We have to do better than that in the future. And we need markets and valuations of those services and storage and privacy and security in ways that are better than what we have now. So there's lots of room both for the technology side and for those who think about all the economics and policy and the regulatory side as well. Now, a fundamental issue with many of the renewables is the question of intermittency. This is the famous duck curve for California, where we have quite a bit of solar in the daytime, obviously. But as the sun gets low in the early evening, this was March 31st. So it's about the time of year that we are now, where there's a big 13 gigawatts of power needs to come on in a few hour period in the early evening as the solar rolls down. Now, natural gas is used for this now. It has lower, but of course not zero greenhouse gas emissions. And so if we continue to use natural gas, which that's one possibility, then we'll need carbon capture and storage. There's also the possibility of energy storage. Lots and lots and lots of work here going on. Part of its materials, what you'd like, of course, is low cost, high energy density particularly for transportation options, earth abundant materials, low toxics, lots of opportunities, but also relatively high cost way of dealing with it. Storing energy in terms of chemical bonds, for example, making hydrogen might be a possibility, but would require a fair amount of infrastructure. Although you can blend a certain amount of hydrogen into natural gas now without changing the pipeline materials. So that's one possibility. So lots to be done here and many, many technology research areas. So let me say a word about transportation. The world is, my own personal view is that we will largely convert urban transportation into battery electric vehicles, but it will take some time to do this. These are big markets and lots of existing, both incumbents in the market and efficient, cost-effective vehicles now. In the early 2020s here, many more electric vehicles are slated to come on the market. Britain and France have said they're going to prohibit internal combustion engines after 2040. China is talking about a deadline. These costs will continue to come down. We're already seeing reductions in battery prices. So I think this competitive market is on the verge of being at scale. But the thing to recognize is that the transportation systems are really big scale now, and there are a lot of vehicles on the world, around the world, And even if you replaced sold only battery electric vehicles, you're still looking at a kind of a 10-year transition period. And I don't think anybody thinks that we'll go to 100% electric vehicles right away. So I think that means that we need to pay close attention to high efficiency engines and greenhouse gas, lower greenhouse gas oil, which you can do partly by using CO2 that would be otherwise emitted to reduce the CO2 emissions associated with oil that's used for gasoline or diesel fuel. So the challenge here is the very large scale system plus the extremely competitive market. But I can tell you, my wife and I both, my wife has a battery hybrid, electric hybrid, and I have an electric vehicle. And they're fun to drive, so they will offer good services that I think all of us will enjoy using. Now, another angle on the efficiency of the transportation side is weight control, and this is just a simple example, but there are additive manufacturing methods where you basically take a powder and form whatever shape you want, then fuse it, melt it in some way to the finished part. Because you're not having to machine a big chunk of metal, and the device can be made in pretty much any shape you want, can weigh less, and if you just look at the same strength of the part, the conventional bracket uses about 3 times as much as the additive manufacturing bracket. So there's some opportunities there that don't seem quite so obvious for when you think about efficiency. So let me say something about carbon capture and storage, and I'll just say that there's a lot to be thought about here. There are kind of two basic angles. One is to deal with concentrated sources, things like power plants and natural gas separations and biomass combustion, fermentation, those kinds of things. Those seem like the obvious first choice because the concentrations are higher, and using various kinds of solvents and sorbents and or cryogenic separations provide plenty of opportunities there. Folks have noticed that our rate of progress toward reducing emissions from the big sources is low enough that we may need at some stage of the game to do direct air capture. This is inevitably more expensive because the concentrations are lower, but many of the same kinds of ideas can be applied. And of course, the natural systems capture very large quantities of CO2 already in biological systems. There are many options for what you do with that CO2. You'd like to make fuels. That would be great. Thermodynamically, it's hard and it's expensive. You can make minerals, or you can store it in the subsurface, and then there are all the biological realm as well. So there's a big landscape of ways that you can manage carbon, and we need to think about this in a much more systematic way. So there's a long history here. Heidi mentioned that in the early days, for me, my career, I had a kind of brief stint as a research engineer at Shell's Bel Air lab in Houston, where I worked on the early CO2 floods in West Texas and Mississippi. And so we've been at this CO2 injection for enhanced oil recovery since the 1970s, and we know a lot about how it works. I've spent a whole career trying to answer questions that were clear to us in the early 70s working there. And most CO2 injected so far has been from natural gas separations because they have to separate that gas anyway to sell the methane. Demonstration is likely to continue. There are projects around the world, quite a few of them. But if we're really going to do this in scale, it's going to need a carbon price that doesn't exist in too many markets yet. So here's an option for doing that with for carbon capture of natural gas. There's a demonstration plant outside Houston I was able to visit about a year ago. Basically what they do here is they use an air separation unit to separate pure oxygen. Then they burn the natural gas with pure oxygen in a combustor. That makes CO2 and water, steam. That runs through a turbine. So you use the CO2 as the working fluid in the turbine. Because CO2 is more dense than steam, that turbine can be quite a bit smaller than it would be for a steam turbine. So there should be some cost savings there. Then you cool it down to knock the water out, recirculate the CO2. Now, you have to take some, you're making new CO2 here, so you have to take some CO2 out of the system in order to have the material balances work. But that CO2 is at high pressure here, and so it's ready to be injected into the subsurface for enhanced oil recovery or for aquifer storage, something like that. And then the remaining CO2 is recycled through heated back up, and so there's a cycle here that produces some CO2 ready for injection. The efficiencies are pretty good. So the very low added cost of CO2 separation, and the cost of electricity is competitive based on projections, of course, at least. Now, of course, they'll have to deliver on that, and we'll see if they do, but it has the possibility. We actually know a lot about EOR. CO2, if you can, if the pressure is high enough, you can displace all the oil where the CO2 goes. So these were experiments and micro models done in my lab years and years ago. CO2 is pretty good. It's low viscosity and it's pretty good at finding the easy flow paths. So the question is here, what fraction of the reservoir can be swept? And in particular here, we now need to think about how to make CO2 flooding less efficient, that is, use more CO2 than the minimum required to recover the oil as a way to maximize the storage as well. Plenty of interesting multi-scale questions to be dealt with here in this, this area. CO2 dissolves in water, and the interesting thing about it is that CO2 saturated brine is more dense than brine without the CO2. Apparently those CO2 molecules can snuggle up against the water molecules in a way that that makes it more dense. So this stuff will stay, have a driving force to go down rather than up, but you still need to have a scale because the dissolution times are long. CO2 is also always more dense than methane at the same temperature and pressure. The molar density is higher. So in principle, methane can be removed from a gas field, oxidized, and put back with volume left over. So there's at least that possibility. You know, and for sake of time, cement and steel are places where CO2 could be captured as well. I'm going to scoot past that and just get to the direct air capture. If we don't move faster than we're moving now, if to have any hope of staying in the neighborhood of 2 degrees C temperature rise, we're going to need to pull some CO2 out of the air. There are people working on this. It's tough. I chose one example here. Climeworks is a company that's doing this. The costs are pretty high, but in principle could come down over time. There's another carbon engineering is a company in Canada that's doing this, and they're intending to try to make fuels. The thing to remember, of course, is that it takes more energy to make that fuel by quite a bit than you're going to get by burning it. So again, it requires very low cost clean energy to be able to do it. Biological systems move very large quantities of carbon around the planet. So looking at ways to boost that, to burn biological materials with carbon capture and storage. There's a big resource there available at what look like could be competitive costs if we're willing to tackle that side of it. So there are some avenues there that can be pursued as well. Otherwise, CO2 markets are mostly small compared to cement and fuels, but they're out there as elements of the portfolio. So just I want to make the case that we need a vigorous research R&D portfolio as well. And I'll just give you one example. This is stolen from my colleagues here at Stanford. But the basic idea here is that if you have the right material, you can choose to have it radiate at frequencies at wavelengths of light for which the atmosphere is clear. And if you do that, then you can cool a device even when the sun is shining in the daytime, just because you're radiating against 3 degrees Kelvin out in deep space. So there are materials that do this, and there's a group here that's been working on, and they've demonstrated absolutely that you can do this. Now it needs to be more efficient, and it needs to be using materials that can be manufactured well, but at the same time, it's an alternative to vapor compression cooling that requires only the energy to do the heat exchange, circulate the fluids in a building, rather than using electricity, for example, for air conditioning. So the world is going to need cooling more and more, and having some passive options to do that better is an example. So lots of other energy R&D to be done. It would be great to make fuels if we can from electrochemistry, and use chemical bonds as storage as well. So lots of opportunities there. So here's my wish list. I'd love to have an efficient, low-cost electrochemical way to make fuels. Biofuels that are cost competitive with CCS would help. There are limits on the total amount of land area and water. More efficient water purification. Storage. Gosh, it enables all kinds of things. If you think about it, really, fuels are energy storage. So having systems that do that better. Better sensors for fugitive methane would be a help. Power electronics in various guises, and very cheap renewable power. And by the way, a price on carbon would help get all of this in place. So let me end here by saying that, you know, even as we're looking at the challenge going forward, we should take some satisfaction in what's been done so far. We have made a lot of progress. Now, clearly we need more urgency, and we need a portfolio approach that's fully stocked across primary energy resources and conversion technologies and systems and timescales with improved efficiency everywhere. And we need to meet the challenge of scale. That's a fundamental aspect of this. But we kind of can see pathways to do a lot of this. Energy efficiency, lots of clean electricity, diversified energy storage, electrifying services, better systems, and deploying a series of new technologies with a vigorous R&D program that can help us do this. So my view is that we humans are very creative when we make up our minds to be. We can do this if we continue on the path we've started, if we increase our ambition now and make a sustained effort over multiple decades to balance human activities and needs with the planet systems that serve us in essential ways. So with that, I'll stop and say thanks for your attention.
Thank you very much for this very interesting, inspiring talk. I'd like to ask the folks who have questions, please text in the chat room because we have almost 100 participants, and I'll go through this chat room and ask either you to speak up and ask your questions, or I would just read your question. So that's I have a question from Dennis. Dennis, I guess I can. I will read. Lynn is Dennis Waskov. He's saying hi, and then now the question is whether he has his kids around, so he's not turning on his camera. So in in your opinion, for the future energy landscape, do we need more methane production or less? And if more, by how much? Or what?
More methane production or less? Is that the question?
Yeah, that's the first part of the question.
Yeah, so it's a good question. My guess is that that in the really long term, we'll move away from methane as well. But I think it will be a very long transition. And indeed, with given that there's large capacity for CO2 storage in the subsurface, I think we should use the natural gas as a way to in particular reduce the amount of coal in the energy mix. We've done some of that in the U.S. already. We, a decade or a bit more ago, 50% of our electricity was generated with natural gas. Now, and I'm sorry, 50% was with coal. And this last year, it's in the mid 20% range. So it really has declined a lot. We need to continue that. That's going to be a challenge in parts of the world that still use a lot of coal. So I'd use the natural gas there to help make that transition, even as we build out the infrastructure to do the intermittent renewables and think about firming in a variety of ways that could involve storage and so on. So I think there'll be an extended period with methane, although I think there will likely be a peak. Well, there will be a peak at some point. The question is when, and anybody that thinks they can predict when the peak of both oil or gas production is
very good.
Good luck, because we've been wrong on that lots of times in the past.
So I'm going through the questions, and I'll do my best to read all questions, though
okay.
We may end up with many. There was a question from Karl-Heinz. Good to see you, Karl-Heinz. Is about the capacity of storage, energy storage. Compressed air energy storage was shown also in one of your slides, and you compared with pumped hydro. How do you compare these sort of capacities? Are they also growing? Where do we stand today?
Compressed air storage has been talked about quite a bit, but there's a very small number of test cases out there. Hydro, of course, pumped hydro is used in a big way now. We do a lot of it in California. If you have a place with a hill and place where you can put lots of water, it has the best round trip efficiencies of any of these by quite a bit, that you can get between 80 and 90% of the energy you put into getting that water uphill, you can get back. So there's not very many batteries that can do that. And in principle, compressed air storage could be done. It just hasn't really been tried at a big scale so far.
Mm-hmm. Very good. And I have a question from Alex, and he's asking you if a more efficient use of fossil-based resources wouldn't still allow us to stabilize the climate issue for the time being, so that we develop further on the other side, on the channel.
Yeah, well, certainly more efficient helps at every aspect for sure. At some point, we really need to get the fossil fuel emissions to be, I don't know that we have to get them to be zero, but we do have to get them to be a whole lot lower than they are right now. So we can get that. I think we can argue about exactly how close to zero you need to get them over time. But if we're going to manage the concentrations in the atmosphere, we need at least reduce total emissions by, if the energy systems generate maybe 38 billion tons a year, we need to get down to well below 20 to stop the increase, and then think about how to get the rest of those systems in balance. So we have a long way to go there.
So I have another question from Sebastian Geiger. Hi, Sebastian from Heriot-Watt is attending. Sebastian says, great talk. Thank you, Morgan. Stanley estimated last year that the cost of the energy transition to reach net zero targets by 2050 will be $50 trillion from hydrogen to renewables, electric vehicles, and CCS or biofuels. In your opinion, what will give us the biggest bang for the buck in this massive investment?
So first of all, I would say, yeah, that's $50 trillion is a lot of money. But if you think about how much we invest annually in energy systems, it's in the trillions. So spread over a 30-year period, it's not crazy. And I think, costs will come down as we go forward. Now, the harder question, of course, is where should we put those dollars? And this is a case where I would make the portfolio argument again, that all of these energy systems have to compete against each other in marketplaces, and foreseeing every detail of that is just not possible, in my opinion. So we need to invest across the portfolio. We need to have it be diversified across energy resources and diversified across ways to convert the energy resources, and then the marketplace will sort that out with interventions on the policy side when it makes sense to do that. So you can see the sort of big broad areas are just the ones that I talked about, but the individual market structures really do matter in terms of deploying, for example, electric power generation resources. So that's extremely heterogeneous around the world. So there's no single answer to that. It's going to be different in different places. Arizona is going to use a lot more solar energy than Alaska, for example.
Yeah, and I have another question from Pachili Zita. After thanking you for the inspiring talk, he's asking, could you give us a sense of which CO2 capture technology is already ready for being scaled up at this moment?
So right now, the most widely used methods are amine solvent capture systems. They're used every day at large scale in refining and natural gas separations. They're fairly energy intensive, and so it would be good to have better ways to do that. In some sense, the fundamentals of separations, the natural gas plant I talked about is one where you've traded separation of oxygen from nitrogen for the separation of CO2 from nitrogen, basically. The one area where I think we should pay attention to the natural systems is in the direct air capture side. The natural systems move our order of 20 billion tons of carbon, of CO2 from the atmosphere into plants right now. You think, well, gosh, wouldn't it? What would we like to have? We'd like to have a system where we use solar energy to capture the CO2, turn it into long chain molecules, and it would be very nice if that system also self-assembled. You go, wait, we have those. They're called plants. So we should be thinking about how to use that judiciously. Like everything else, it can't be the only thing we do. We have to do that in a way that doesn't disrupt the natural systems too much. But there really is, because they're big systems already, there's something to be done there. So there are a variety of sort of advanced materials kinds of ways of captured, ionic liquids, metal organic frameworks, various sorbent systems that are underway. But the ones that are used right now, big time, are all amine solvent separations.
We have plenty questions. I'm gonna ask a bit more. I hope that I go through all the questions. We'll see if we can manage. There is a question from Ruhi. He says, do you think generally that the economic growth and lower greenhouse gas emission are compatible?
Yes, I do. I think it's crystal clear that we'll need to think about people who are working in areas where there are fewer jobs, but there will be new jobs associated with all of these technologies, and building these and maintaining these systems will provide plenty of economic activity. And I think you look at even places like California, where we've had some stringent rules in place for a while. We've been able to do this and keep a vigorous job market as well. You know, I'm reminded back of the situation in the 1960s when we were having this argument about air quality and water quality, and the arguments against restricting air pollution emissions, for example, were that it would cost too much and that competitors wouldn't do it and it would bankrupt the economy. Pretty much the same words you hear sometimes now. But California put some rules in place, and some other states went along, and pretty soon industry was in Washington saying having 50 different sets of rules is not okay. And so we put the Clean Air Act in place, and here we are 50 years later. We haven't solved every problem, but it's a lot better than it was, and we didn't bankrupt the economy. So I think we can do that again.
Yeah, that's great. We have a question from Majid Sanizadeh from Utrecht University is with us. Hi, Majid. He's asking, you talked briefly about energy storage. For larger scale green energy systems, we need larger scale storage with fast retrieval time of the retrieve of the energy from the storage. Where are these options?
Yeah, so there's an interesting cascade of scales here. So what you need for energy storage for putting on a vehicle, for example, is different from what you need for utility scale. On some time scales, shifting demand is every bit as good as storage. So demand side management approaches can alleviate part of the intraday variations that we need to be able to accommodate. You know, supercapacitors and flywheels can do the millisecond variations from wind turbines. So there's a variety of scales here. The really big scale systems, the winter, summer, or multi-day storage, those are the hard ones. Hydro can do it, but it would take a whole lot more hydro in a lot of places, and those are not without impact as well. So this is a place where it's just not clear exactly how this is going to play out, and there's room for lots of R&D there as well. I know I didn't really answer the question, but the trouble is I don't know the answer to the question. So it's a good area for research.
I have a question from a colleague called Arvind. He's asking, after thanking for the talk, he's saying, how do you see the future of IGCC technology, the integrated gasification combined?
Yeah,
I would say.
You know, the IGCC was really thought about as a way to be able to retain some coal in the mix. It has just really had a hard time competing. The couple of the big plants that have been attempted in the U.S. Have not performed in a cost competitive way, and I think, I mean, there's no question that we can do it, but I just give you the example of a plant in the Kemper plant in Alabama, where they started out to gasify coal. It was a complicated plant that had sort of five chemical plant components within it, and problems with all the coal handling it in the high pressure injection. And and they just never could get the thing to balance and work in a way that could compete with natural gas. And so they've switched to powering with natural gas there. So I'm not optimistic that IGCC is going to continue in a big way.
I see. Okay, Ali Eftekari from Denmark is asking, thanks a lot for the talk, a paradigm shift in the fossil fuel conversion from combustion to direct extraction of energy from chemical bonds in the fuel cells significantly increased the efficiency. Where else in your wish list do you need a paradigm shift?
Well, so it's a good point that fuel cells basically have the advantage of using electrochemical methods to boost the efficiency. I would say that the general area of electrochemistry, catalysis in the sense of being able to design catalysts that do what you want them to do, all combined with the ability to control structures at very small scale, say nanostructured materials. That opportunity space has never been bigger, and I just think that there's a huge opportunity to do energy conversions that are efficient and reduce carbon emissions in lots of good ways using electrochemistry, basically, and that's what fuel cells do. So we just we should put lots of effort into that as we go forward.
I have the next question from Jaap Vlugel, is mentioning lots of nice developments were mentioned in your talk, but how about the power challenge? Who determines which path we all will follow? Is more government?
Yeah. Well, so here's what you do. You appoint me as king, and I'll make all the decisions. How about that? Might not happen. So yeah, so it's a good question, and you know, there's something to be said for the diversification that happens with different groups competing here. And as I said before, we don't want we want a diversified system that has lots of resources and conversions. And the ways we've done that in the past is by markets and providing a market structure that can do this. And that, I think, is more efficient than having an energy czar that would make all the decisions. And the competition will offer ways to do it. It can be messy and it's hard to foresee, but that's how we've done it in the past.
Do you see government intervention as well playing?
Well, governments have an important role to play in a variety of ways. One is in, for example, providing incentives. That's had a big effect on wind and solar in the United States, at least. One is in demand pull, that is, they can purchase when the U.S. Postal Service buys all electric trucks for running around. That's going to move the market. So governments they set the rules in which the competition takes place, and they also can push things along. I think the goal is getting to down the learning curve in terms of scale, and there is an important government role there.
Steph, why don't you ask your question yourself? Let's just try it.
Yeah, I can try. Yeah, I think it's only partly answered, I think, some of the questions. My question was basically related to what's the main bottleneck to speed up the energy transitions on the relatively short term?
Oh, main bottleneck.
Steps
I would say it's these pesky humans that, you know, if only we were rational actors. And the example I would give is that, you know, there's just abundant evidence that energy efficiency pays for itself at all the scales, you know, the individual household scale all the way up to big businesses and governments. And yet we move more slowly than would make economic sense to do it. And you can ask why that is. it's partly paying attention. We have lots of things to think about. It's partly just inertia, and so we just have to keep paying attention to it. But this is another aspect where it's really the portfolio. You know, we need work on the regulatory side. We need work on the market side. We need a variety of work on the technology side. So let's invest in the portfolio.
I have the next question from Anke Dahlman. What's your view on efficiency and scale, going towards centralized high efficiency systems or local distributed lower efficiency?
Yeah, it's a good question. You know, I think it's a balance. There's going to be room for both of those kinds of things. And so, for example, think about some small village in Alaska. You know, that's going to be a place where an energy system that works at the scale of the village is going to make sense. In San Francisco or Los Angeles, the systems are different, and even if you're going to let's say a more efficient district energy system, it takes a lot of infrastructure to do that. So this will be a set of trade-offs that will get made, and I don't think there's any single answer to the question.
And I have the next question from Daniel Wong. He's asking, how do you see the current collapse in oil price would impact the energy transition movements?
If I knew what was going to happen on oil prices, I would be much wealthier than I am. So whenever somebody asks me a question about what the price of oil is going to be, I always say, well, you know what, it's going to go up and then it's going to go down, but not necessarily in that order. And so the part of the situation right now with regard to oil is temporary. You even just moving the demand side of the market by a couple of million barrels a day is enough to really influence the price of oil. The marginal reaction to that demand change can be significant. We've reduced demand by about 10 million barrels a day, so that's a lot. Now that's coupled with the fact that in the U.S. mileage standards are taking hold. Our administration is trying to change that, but demand has been flat, so you can move the price of oil a lot. I think once we're back at a level of economic activity that uses transportation fuels in a bigger way, you'll see the price come back up. But there's excess capacity in the world. This is not the first time it's happened. So we may be in a period of low oil prices for a while, which will reduce the incentive for enhanced oil recovery, for example. In the long term, I think it's reductions in demand that reduce the use of oil in the future. But I have no clear view of what the timescale for that is.
I have two more questions to cover, and we still have 60 people here with us, so I'd rather go through them because this
Sure.
hour is quite interesting, and we receive plenty diverse type of questions. I have a question from Charles, our graduate student, and I remember, Lynn, you have been advising us always include the students in whatever meeting you are going through. So Charles.
That's the way I like. Yep.
So Charles is asking, how do you see this in developing economies? In developing countries, governments are more responsible also for developments, and any taxing or any energy transition would be seen as a harder towards growth.
Yeah, it's a really good question. You know, the world of changing energy systems in places like Europe or the United States, it's very different from thinking about what needs to happen in Africa, for example. And so we need to we need to provide, I think, assistance to governments in places that are building new energy systems, because we shouldn't encourage them to repeat the same long, convoluted pathway that we took. We should take advantage of things, and in particular, if you think about places like India and Africa, where just providing a sort of basic set of energy services with electricity improves lives quite a bit, with some combination of lighting and pumping water and so on. That's a place where distributed systems can be done in a way that really do make sense. And then over time, as those systems build out, then a more connected grid-based system would make some sense. Doing this in ways that allow market services at low cost of entry for individuals, I think makes an awful lot of sense. And so creating market structures that can do that makes a lot of sense. It's a different set of challenges, and smart people should be working on this. I know that, there's some groups at our business school and so on that are trying to think about all this as well. And I would really encourage that, because what's not okay is to say to the developing economies that, I'm sorry, we used up all the atmosphere, so you don't get to play. That's not okay.
Great. Okay. So a colleague, Ramon Hansen, a colleague of mine, he just asked me to thank you. And he was reminding you that you both shared a flight to Denver many years ago, and he was happy to see you here today. So I just wanted to mention that also.
Oh, thank you.
And to all others who are with us still, I posted a link to a Surfdrive where you can download a copy of the slides today to go through this if you or your notes as well for future references. Let me thank Lynn again. It's quite hard to clap for someone, I guess, online. We should invite, I don't know, maybe we can just go to our cameras now on and see if we can just...
Well, thank you all. This was fun. And I can tell you, having done this sort of thing sometimes in the past, being able to see some faces really does make a difference. So thank you all for those of you who had your cameras on. That's great. Thanks for that.
But we should thank you also for this inspiring talk, especially spending several hours over the weekend to make sure this online conference would work. Thanks a lot, Lynn. Keep well, everybody, all the colleagues. Have a nice evening here in Europe and morning in the US, West Coast. So all the best to all. Thank you very much.
Okay, same to you. Bye. Thanks again. Bye-bye.
Thanks, Adi.